would not have been possible. So what are the various sectors we need energy? There are four major sectors we need energy. If we divide in these four areas: domestic or oblique offices, industry, transportation, and military. Whatever the areas of energy required, it will come under this four category, right? And what are the forms of energy, basic forms of energy? There are various forms of energy, but two basic forms of energy are very popular and widely used. Those are basically thermal or heat energy, and second one is electrical energy. Heat energy is, extracted basically renewable and non-renewable from both the, sources. So non-renewable mainly is consists of basically coal and petroleum. We burn it by a combustion of coal and petroleum, maybe liquid fuel as well as gaseous. You can extract heat energy. And renewable is solar and biomass. Solar is, I am talking of solar radiation, which is basically trapped, and in the forms of solar heater, using a solar heater, we trap the energy and get the heat from the radiation. Similarly, biomass is basically, I'm talking of vegetation, plants, etc., which gives us energy when we do the combustion. But solar energy is purely, it is pollution free, clean and green. On the other hand, if you talk about a biomass combustion, it releases again this polluting gases, and residue will be left over as a solid residue which pollutes our environment. But solar is clean and green. So if you see the heat energy, extraction of heat, getting heat from these sources, renewable, non-renewable, solar is the clean and green in nature, right? But coal, petroleum, biomass still, it occupies the largest share or large share when you talk about the heat generation from a fuel. Even nowadays there is a solar heater. You can see many domestic or offices they are using the solar heater to extract the solar radiation, to trap the solar energy, and as it is a clean and green in nature. However, initial cost is very high. Initial installation cost is very high. Once you install it, then you can recover the cost over a time period. But the main problem, main advantages rather, you can say, is it is a clean and green nature, green in nature. You are not polluting your environment. But when you say that biomass combustion or coal or fuel combustion to get the heat, you pollutes the environment. So we have to switch it over to renewable from non-renewable energy resources. Now, if you talk about electrical energy, electricity you get either non-renewable or renewable. Non-renewable, what are the sources? Again, fossil fuel-based thermal power plant. You do the combustion of fossil fuel, whether it is a coal or oil-based plant, then you get the thermal energy. Then thermal energy is transferred to a water to get the steam, and then from the steam we get the basically the steam is used to rotate the turbines, and we get the thermal power. But the main source of energy is basically the fuel, fossil fuel, again non-renewable. Now another source is battery technology. Battery technology, it may be primary and secondary type. Primary type, use and throw cell, right? And it is a non-renewable nature. Similarly, secondary batteries are also non-renewable. Until unless you charge it, you cannot get back the energy again from the battery. So these are not basically preferred nowadays, or government is giving more emphasis to get energy via renewable route, as those routes pollutes either no pollution or less pollution, you can say, in comparison to non-renewable, because non-renewable pollutes our environment in many means, various ways. So renewable, if you talk about this renewable energy resources, so solar, photovoltaic, which basically utilizes the solar radiation and get the energy. Then wind energy, similarly, wind turbine is there. Kinetic energy of wind is used to rotate the turbine, and we get the energy using a generator. Hydropower, power which is in the form of kinetic energy. which is stored in the water due to the potential water head, we convert this kinetic energy to electricity again using a hydro, that is called hydropower. So all these are renewable in nature. If you see these three, solar photovoltaic or wind and hydro, this never pollutes, environment. However, it says, and many literature it is mentioned, that hydropower, to some extent, it's damage our environment. It creates ecological imbalances. When dam is created, without dam, you cannot have a large hydro plant. Okay, so that damage basically to some extent our environment. Like Tihiri Dam, when Tihiri Dam was created, a lot of natural habitat were lost. We do not consider all those factors, but if you go into depth, then you can see there's a lot of damage to our environment. So that is another concern. But other way, it is, you can say there is no pollution or less pollution. Fuel cells is another class of energy device. It is renewable in nature. When you talk about hydrogen-based PMFC or ethanol or based fuel cell, ethanol is renewable in nature. Hydrogen, if you produce via electrolysis of water, then it is renewable in nature. And simply it is fed to the cell, and you can have electricity. It's like just like an IC engine, but the mechanism is electrochemical methods, which basically with the help of electrochemical reaction split the hydrogen molecule, and then get electrons and H plus ion. Then electron basically blow up electron from one electrode to another. It gives the electricity, and that's why it is renewable in nature. And world is now concentrating on this technology, that is fuel cell technology, because it is if it is a hydrogen based, there is no pollution at all. The electricity as well as water as a byproduct will be produced. There is no other emissions. But if you burn hydrogen as a fuel in a combustion engine, apart from heat, energy, water molecule as a product, you can have a NOx formation, because you cannot avoid nitrogen when you burn fuel in an IC engine. Nitrogen will be there with the air. So NOx formation and high temperature is unavoidable, and NOx is a polluting gas. Okay, so that's why switch over to from combustion of a fuel non-renewable to the renewable, or this fuel cells type technology could eliminate or reduce the pollution problem. Okay, and it can give you the energy in sustainable manner. So if you look into the broader spectrum or broader aspect of energy supply in India, in Indian perspective, about 70% is still now non-renewable, and 30% renewable energy it provides. And government is planning to increase more renewable and reduce dependency on non-renewable energy resources, because supply of energy non-renewable is limited, right? Devising a sustainable energy resources that are readily accessible to all the nations, environment that these are the criteria: environmental friendly, cost competitive with the fossil fuels is the greatest challenge, right? It must be accessible to all the nations. This is another criteria. Okay, so that kind of technology we must have, and that is a big challenge to the to the scientists in this 21st century. And as I have already said that fossil fuel, we are still dependent on 70%, because non-renewable sources provide 70%. We are dependent on this non-renewable to get the energy, and 30% on renewable. And this higher rate of fossil fuel consumption and as limited reserves, and also it emits SOx, NOx along with CO2. These are all global warming gas which pollutes air, right? And therefore we are, all the scientific community is trying to switch it over to some sources which will reduce the consumption of fossil fuel and reduce the pollution as well. So what I have decided in view of this, that waste material which we have already, and you cannot avoid the use of those material, and finally it is thrown as a waste. And if you can use those waste material to get back the energy, because those material is waste, but it is an energy material. You can convert via some technology to get some fuel, and fuel like chemical or material, and that will give you energy again in the form of electricity or in the form of thermal energy. So waste material via chemical route I shall discuss. That will really enlighten you, and you can think on it for future research as well. Okay. And second one is renewable chemicals I have considered here, which have a huge potential to give electricity directly via electrochemical route. So one is waste material via some chemical route to get some fuel. So you are minimizing waste material and getting a better quality of fuel, which can be used in a IC engine directly, right? Just like a gasoline or it's a similar petrol or gasoline are same, and diesel like fuel. And second option is renewable chemicals like ethanol, glycerol. These are renewable. We can produce as much as we want using a biomass resources. Okay, and then using this certain technology like fuel cell, you can via electrochemical route, electrochemical conversion, you can get the electricity directly, right? Now, if you see the many journals or news nowadays, there is always, you can see that hydrogen energy. Okay, our government is also trying to focus on hydrogen energy and to make India as a hub of hydrogen, right? To provide a world globally this hydrogen fuel. So to make India as a hub of hydrogen gas, production of hydrogen gas, it's a mission of government of India. So it is a mission mode project launched by our honorable Prime Minister PM Mr. Narendra Modi, and during this 75th Independence Day lecture from Red Fort, that India will be made as a hub of hydrogen, world hub of hydrogen rather, you can say. So it's a big announcement, I can say, which will motivate us to work on this hydrogen energy or hydrogen gas production in cheaper way and economically and in sustainable manner. So shifting to hydrogen economy may reduce dependence on fossil fuel usage and greenhouse gas emission. The key technology enabling hydrogen economy are, what I would say, pyrolysis of waste plastic. So waste material, I have considered here plastic material, waste plastic, to produce fuel range hydrocarbon, and fuel cell technology, which can use we can use alcohols like glycerol or ethanol as a fuel, renewable fuel, and hydrogen as well, and then convert it into electricity directly, right? It's a battery, similar to battery, and I shall discuss fuel cell in detail. The first part is pyrolysis of waste plastic. Why? Because plastic is what is the origin of plastic? Plastic originates from petroleum. It is a petroleum products. Monomer of like ethylene, it gives you polyethylene. Okay, monomer of propylene, it gives you polypropylene. Monomer of polystyrene, it gives you polystyrene after polymerization. So all the monomers we get from the different types, some liquid hydrocarbon, petroleum products, and then they are polymerized to get like polyethylene, polypropylene, polystyrene, polyethylene terephthalate, polyvinyl chloride, and polycarbonate. All these, polymers, right? These are known as a plastics, and these plastics are highly demanding. You cannot imagine life nowadays without plastic. There is a ban by government. Don't use plastic, and government is trying its best, but not able to stop the use of plastic, because there are certain advantages of using plastic. I shall discuss later on. So if you say what is plastic, plastic are synthetic organic polymers of high molecular mass synthesized by polymerization of petrochemicals, like hydrocarbon, that I told different monomers. So these are the various plastics like PET, HDP, PVC, LDP, PP, PS, and others. They are designated by certain numbers. If you see some bottle and if number 1 is written, within this symbol, then it's a PET, polyethylene terephthalate. This is a material. If 2 is mentioned in that bottle with this, if you see the bottle below, then it is HDP. Similarly, PVC. If 3 is mentioned over there within this code, you might see, and without even if they don't mention the name, then from this number coding, you can say what is the raw material used for this particular stuff. Now, reasons behind the use of plastics: lightweight, durability, faster rate of production, design flexibility, and low cost of production. These all I'm not going in detail. However, these plastics have many demerits. Non-biodegradable, right? Pollutes water, air, soil. In other words, this damage environmental badly. So let's say plastic means polyethylene carry bag. Once it is, you are carrying some items from a shopping complex or from some groceries, you have brought some groceries, you are carrying a poly bag, carrying at your home, bringing it to your home. Then what you do after using, you throw it. You can see daily at least 1 or 2 carry bags you throw after reuse. Now, what is the consequences? Final consequences. You throw it, and then municipality people, they carry it and then dump it in the dumping ground, and it is non-biodegradable nature. So huge amount of plastic it is dumped over a time period. So what will happen? So one is soil pollution will take place, and if it is incinerated without recycle, this you can see huge pile of this various type of plastic. These are dumped. If it is not recycled, and the percentage of recycle is very, very less because of problem of collection and segregation and all, because we don't have habit to segregate it at our home. We just mix it and put in our dustbin, and that dustbin again dump we hand over to the this corporation people when they collect it. Okay, so we do not have a segregation method. That creates a problem. Okay, and that when we say the incineration, that when there is a huge dumping, huge amount of plastic is dumped and there is no space, what we do basically, we burn it, incineration, to reduce that volume. And incineration creates air pollution, and many times that plastics washed away and mixed go to the water body, and then what happens? That pollutes the water body. Water that floats on the water surface, and aquatic life is greatly affected, right? Sometimes they block the drainage system of the city as well, and we see that there is a flood. So shorter duration of rainfall, you can say there is a flood, because it blocks the our drainage system badly. So therefore, there is a need for developing some sustainable method which could reduce this plastic waste or alter to some value-added products. Okay, like lighter paraffin of diesel or kerosene range, and sometimes you can say gasoline range. It is also found. Other chemicals like benzene, toluene, ethyl benzene, xylene, that could also be produced from this waste plastic material. Okay, so pyrolysis is the technique. Pyrolysis of plastic, pyrolysis is a process which could convert this plastic waste to valuable chemicals as well as fuel range hydrocarbon. I shall discuss about this later on after discussion on these various chemicals which could be produced, like benzene, toluene, ethyl benzene, and xylene. What is the use of benzene? Benzene, it is raw material for styrene, phenol, cyclohexane, nylon precursor, right? Gasoline blending for improving octane number. So toluene, remember toluene, ethyl benzene, and xylene, they are blended in a fuel like gasoline as well as diesel. For gasoline, it improves the octane number. However, for diesel, we cannot avoid this ethyl benzene, xylene, and toluene, as the boiling point is similar. The boiling point of these three aromatics is similar to the boiling point of gasoline, diesel hydrocarbon. So diesel is nothing but it is a consists of paraffin, mostly C16. So carbon atom is C16, okay, and that percentage will be very, very high. So that's why diesel is characterized by the Cetane number, okay. Similarly, the gasoline is characterized by octane number, percentage volume of isooctane in a mixture of isooctane and N-heptane, which gives the same ignition characteristics as the fuel under consideration is tested in a standard CFR engine, cooperative fuel research engine, right? And that will give you the same NOx. So octane number means gasoline, okay, and for diesel engine, we this number is very, very important. That is Cetane number, right? Higher the Cetane number, better is the fuel quality. Higher the octane number, better is the gasoline quality. Next is ethyl benzene. So to manufacture styrene, which is used for polystyrene again as a solvent in gasoline as well, right? It is used in production of plastic bottle, polyester clothing, etc. as a solvent with a range of application from circuit boards, cleaning, varnishes, etc. So these are the few chemicals, or you can say major chemicals we can produce from the waste plastic via certain techniques, not only pyrolysis. So I shall talk about, along with pyrolysis, we can do aromatization, selective cracking, as well as in situ aromatization, which can give you this important major aromatics. If you see the current status of disposal in our country, more than 5.6 million tons per annum plastic is generated as per CPCB report. Though it is old, and this has increased to a large extent, but 2013 data as it is published, what I got, it is 5.6 million tons, and only 10% is recycled, very small amount. Otherwise, rest is incineration and landfilling mostly, okay. So there is a huge scope of conversion of this plastic to a valuable fuel. So plastic waste contribute to the solid waste around 8 to 15%. If you see the plastic weight, Government of India 1997 data, okay, so 8 to 15%, right? And if you see the plastic waste generation is higher than the recovery, so there is always huge gap. If you see 2000 and 2015 data, there is always a gap between plastic waste generation is higher than the recovery. So rest remains in the environment as a waste. So 4 metro cities in India, major metro cities, if you see Delhi, Mumbai, Kolkata and Chennai, 689.5 tons per day is generated, and uncollected is 275.5. Only a small fraction is collected from the waste. Otherwise, all they are uncollected. Littered plastic, it remains. Tons per day, it's a huge amount. 408.1 in Mumbai, then Kolkata, and Chennai is 429.4. So you can see in all cities, littered or uncollected plastic is huge amount. They remain in the environment as a waste. As I am living in city of Varanasi city, right? So I am much more concerned about my city, that what is the status of plastic waste generations here. So municipality solid waste of Varanasi, its analysis shows that plastic is 22%. There are various types of waste material, food waste 32%, textile 10%, and rest you can see paper, cardboard, glass, ash, leather, etc. But 22%. Out of 22%, it is seen polyethylene is 41%, which is very, very high. Then polypropylene 24%, PET 13%, right? And polystyrene 7%, right? So if you see 4 plastics waste we are talking, their percentage, right? Polyethylene, polypropylene, polystyrene, and PET. That can be, there is a huge scope to convert this plastic material, waste plastic, to valuable chemicals. So polyethylene, polypropylene, and polystyrene was selected here as a major raw material, plastic waste from various types of plastics, as their percentage is very high. But PET not considered because it creates a problem of benzoic acid, when it is broken down by thermal pyrolysis. So benzoic acid is a byproduct which basically choke the condenser and create that creates the major problems in collecting the products. So that's why it is not recommended to do pyrolysis for the conversion to get the fuel like hydrocarbons. So polypropylene, polystyrene, and polyethylene, that's why could be considered as a good source of as energy material waste, but energy material to get the fuel like hydrocarbons. If you see, this data is really scary. 800 tons per day in Varanasi, it is produced, and out of this 0.217 per capita, waste generations, plastic waste we are talking, means not plastic exactly, MSW waste generation. So per capita waste generation is 200 grams per person per day. It's a huge amount. And then accordingly you can find out the percentage of plastic in that waste. Not only major cities, also high altitude mountain areas also badly affected. High altitude mountain areas, okay, plastic waste are thrown by tourists, local resident, and military people. However, no such studies have been performed on plastic waste generation and pyrolysis for high altitude area. You cannot see any literature that specifically for high altitude areas this has been particular recycle or some conversion techniques or management, solid waste management technique have been adopted. No such literature is available. Only some published article by news agency like Hindustan Times in 2018, they published a Himalayan mesh growing garbage pile, a threat to mountain ecosystem. So on World Environment Day, 5th June, volunteers of 200 organizations picked 4 lakh pieces of plastics in 2 hours of our operations, right? Himalayan states of Sikkim, Meghalaya, up to Kashmir, right? So this side Manipur, Assam as well. So this northeast, this area, Himalayan belt, when there is this operation of 2 hours, so this much of plastics was picked up. Now mostly it has seen that it's a plastic plates, cups, chocolate wrappers, juice, chips packets, etc. Tetra Pak also found large amount. So we talk about plastic, but there is a scope of working on Tetra Pak as well as a feedstock, waste material to convert into valuable products. So waste material, PS, PP, and polyethylene, again we can focus on it to convert into valuable hydrocarbon. Now, plastic waste management method, what is our common methods adopted? Landfilling, largest amount, 79%. Combustion, just burn it and reduce the waste, incineration. And 9% only recycle, 9 to 10%, I told you already. Landfilling requires space, non-biodegradable, and hence polluting soil, water. Energy content in the plastic is lost when we dispose it. Many times cow and dog some eat and it's a harmful for them, right? And we have seen many times that animal dies when they consume it. So we have to be very careful, and we have to reduce the landfilling because of this demerits or this negative impact on environment or as well as human health and animal health. 12% incineration. Incineration is nothing but combustion of plastic, and combustion, lot of combustion means there will be emissions of pollutants along with aromatic polycyclic aromatic hydrocarbon. Which accelerates global warming, right? Recycle, as I told you, recycle is the most effective way to deal with the plastic waste. Its effectiveness is highly dependent on public awareness and economic viability. And many plastic can be recycled and materials recovered can be given a second life. And this method is not fully utilized due to the difficulties with the collection and sorting of plastic. In India, you hardly see this type of color code that Okay, you throw, glass in the red one, plastic only in the, green one, paper in the blue one. Okay, and then general one in Ivalo. We don't have this color code and this type of dustbin. Nowadays, you can see green one, but we dump all together in the green one, right? Only we have a biodegradable and non-biodegradable. That is also not seen in everywhere. So common method nowadays, you can another method, not it was tried from the beginning earlier. It's recently started few years back. You can say 10-15 years back, that plastic can be converted efficiently via this pyrolysis route. Okay, thermochemical decomposition. So what is pyrolysis? Pyrolysis is thermochemical decomposition of material uh, at elevated temperature in the absence of oxygen. It involves simultaneous change of chemical composition and physical as well. There are two types of pyrolysis, thermal and catalytic pyrolysis. Thermal pyrolysis, it needs only the temperature, high temperature, no catalyst is required, right? But temperature required is very, very high. Impurities in the liquid fuel will be more because it is non-selective pyrolysis. Wide range of products you can have. You cannot have your target molecule. So if you want to say, if you do the thermal pyrolysis to get the liquid fuel, so liquid fuel will have a wide range of, varying range of components, not a selective components. And that is not suitable for the use in IC engine like diesel, DG set, or gasoline engine, right? Gases will be produced less quantity. CO2 in high concentration might be there. Char will be there, high quantity char at low temperature, right? This is for the thermal pyrolysis. However, the catalytic pyrolysis have certain benefits over thermal pyrolysis, although you need additional, component, that is catalyst. So what are the benefits? At the expense of catalyst, you can, have several, benefits, and those are less temperature required. First of all, temperature requirement is low, and less energy. That's why temperature requirement low, less energy is required. The liquid yield which you will have selective, means if you want to have a gasoline range products, you can select your catalyst, you can fix that your process parameters, and the product which you will have a liquid fuel of gasoline range. Or by modifying the catalyst process conditions, you can have a better quality of fuel, like a diesel like fuel. You can do the more aromatization, so aromatics content will be high. So this way you can change the product composition by selecting this catalytic pyrolysis route. Increase the production of gases. Gas contains C3 and C4, propane, butane. Decrease the char formation. Here char formation will be lower than the catalytic thermal pyrolysis. So that's why catalytic pyrolysis is preferred over thermal pyrolysis. What is the mechanism? First is the chain initiation reaction. If you have a this polymer, so this will form free radicals, and these free radicals which is formed will, in the second stage, during the propagation reaction, through these various reactions, depolymerization through beta session, then intramolecular hydrogen transfer, or intermolecular hydrogen transfer, right? So what you can see, just try to understand, the free radical which is formed, like this is the free radical. So two paths you can see. One is another free radical, and second olefins, okay, unsaturated hydrocarbon or unsaturated hydrocarbon, and you can see another free radical. So in two different routes, two different types of unsaturated hydrocarbon and free radicals again you can have. So intramolecular arrangements, if you see that hydrogen transfer from one location to another location taking place, right? So here it was a free radical. Free radical is at the center now. Hydrogen has been transferred to other location. Similarly, intramolecular, if you see, then between two molecules, right, and one, you can say radical and another molecule, okay, hydrocarbon molecule. So intermolecular, this hydrogen transfer takes place. So RCH3 dot, it is RCH3. Now product has formed, alkane has formed, and another radical, free radical has formed. So intermolecular hydrogen transfer. So this way you can have a various types of saturated and unsaturated products. Now chain termination reaction, you can see earlier that radical is there. So if radical is there, further reaction will take place. So two radicals will combine, will give you the final products. This is a chain termination reaction. So two radical again give you another product. So this also will give you two different types of product, one saturated, another unsaturated. This way you can have various range of product from the free radical which has been formed in the chain propagation reaction. Now aromatization is another process, okay, that if you know the mechanism, that you can control by selecting the shortened method, by designing a reactor, as well as selection of suitable temperature range, as well as catalyst. Now if you have a alkane, saturated paraffin proteolysis will give you carbonium ion. This carbonium ion through cyclization will form naphthenes, and dehydrogenation of naphtene will give you unsaturated aromatic, that is aromatic hydrocarbon, unsaturated hydrocarbon, that is aromatic. Similarly, beta scission will give you alkane or alkene, okay, but lighter hydrocarbon. But aromatization is a very good technique which will upgrade the fuel, right? That's why I told you benzene, toluene, ethyl benzene, and xylene, if you want to produce via this pyrolysis and followed by aromatization is required there. How to select that which plastics is suitable, right, for pyrolysis? That there are certain criteria, right? What are those? For polystyrene, it is a good, very good for pyrolysis, gives excellent fuel. Low temperature is required, produces less viscous oil as compared to polypropylene. Similarly, polyethylene, no problem, very good for pyrolysis. Polyethylene also, this is polyethylene, and then polypropylene. But polyethylene terephthalate and PVC not suitable because it produces benzoic acid, polyethylene terephthalate, and PVC, polyvinyl chloride, it produces hazardous chlorine gas. So that's why not preferred. Okay, and even if it is in the mixture of a plastic and you would like to perform pyrolysis of plastic waste, you should avoid. So these are the few literature survey on thermal pyrolysis of polyethylene, polypropylene, and polystyrene. So all these you can see polyethylene, polystyrene, and polypropylene, where 93% is liquid yield, 97 and 92.4. But the problem is it's a non-selective and wide range of product is there. So that's why not suitable. If the product is analyzed, the liquid product I'm telling, you can see that various type of impurities are there in terms of aromatic hydrocarbon, which might create problem in the engine or carbon deposition, right? But catalytic pyrolysis, this literature shows that polyethylene LDPE and then polypropylene and polystyrene, okay, and where 93% you can see the liquid yield. Here liquid yield is little lower, but quality is better. It is seen that although liquid yield sometimes it decreases, but you can see the quality wise it improves a lot. You can see the temperature is lower than the thermal pyrolysis, obviously. So from this literature survey, thorough literature, what we have observed, that plastic waste pyrolysis for the BTX, no such paper is found. BTX, okay, benzene, toluene, ethyl benzene, xylene, or fuel for generator set not been studied. And reactor design, like no such detailed study on reactor design and process parameter is found in the open literature. And third one is, many paper have concentrated on commercial catalyst ZSM5, but there are many natural catalysts which could be used effectively in place of ZSM5. So that possibilities has also been explored through this study. So to produce low paraffinic fuel-rich hydrocarbon and BTX from waste plastic. Two major areas are considered here. One is reactor design and catalyst arrangements within the reactor, and second one is catalyst type. By these two, controlling these two parameters, or you can say two aspects, you can control the product distribution, or you can control the quality of liquid fuel. So these are the few objectives through which we can reach our goal. Production of BTX mainly, as well as fuel range hydrocarbon. First is plastic waste after collection. What is done? It is cleaned by washing, with water, then drying and shredding using a scissor. But when you talk about industrially or commercial production of fuel oil from plastic waste, then there must be shredder machine, right? So then a pyrolysis, you should go for pyrolysis. Second one is catalyst, ZSM5, commercial, as well as fly ash synthesized catalyst. There is a red mud or river clay that can also be used, but we have taken here fly ash. So we have studied all, but I will show you the fly ash and compare with the ZSM5. So ZSM5 is, the synthesis method. I have this chemical, only the reaction I have shown here. So ZSM5 is the product, silica, sodium aluminate, sodium hydroxide, and this fourth one. Okay, if you combine them, then you can have ZSM5. But the main problem with this, sodium, it is a basically sodium ZSM, it is called alkaline. Sometimes more aromatics or aromatization or alkylation, then you have to modify the catalyst. Then it is converted to hydrogen, HZSM. Okay, and based on your need, you have to treat the catalyst. But this is the simple technique to synthesize catalyst from natural material. And I'm not going in detail of that catalyst because of shortage of time. ZSM5, okay, if you this is nothing but silica alumina, of course, and pentasyl structure. This is the pentasyl structure, molecular shapes. And if you see the literature, the pores are very, very important. You can see these are wall of the pores, and this dimension is around 0.472, 0.472, around 0.56 nanometer. I hope you understand. 0.6 nanometer. It's very micropores are there, so it is known as the molecular shapes. Only the molecules which are lower than the size of the pore, then only those molecules will enter and will react, right? So that's why you have, if you know the size of the pore and if you know the size of the molecule, which molecule will enter, you can control yourself, right? Next is fly ash. Okay, as I told you, fly ash is another raw waste material where there's a huge scope to produce catalyst from this and use it for pyrolysis in place of ZSM5. Is there any question? Actually, I cannot see on the screen. If you have any doubt, I can stop in between, please. No.
Sir, we will take the question at the end of the session.
Then it is okay. I think I should proceed, right? Thank you. Sir. So in India, 184 million tons per annum. 184 million tons per annum. Fly ash is generated from thermal power plant. It is the data of 2014-15. And in UP, Uttar Pradesh, highest amount, the maximum amount of fly ash generation, 24 million tons per annum. So I think it's a huge amount, right? So this fly ash is a waste. Nowadays, brick is also manufactured from fly ash. But if you can generate or produce catalyst from fly ash, waste fly ash, and it's a big achievement. I think you can replace the commercial catalyst ZSM5, which is expensive, highly expensive. So silica fly ash consists of basically silica, alumina, iron oxides, magnesia, calcia, and mainly silica, alumina, Fe2O3, and magnesia, sometimes calcium oxide. If you see in this range, but this is the activity of the, as a play catalytic role up to this calcium oxide. This type of natural material, when you talk about clay or red mud, that also consists this type of mineral matter. But silica and alumina is used widely as a catalytic as a catalyst for the pyrolysis of plastic waste. Okay, so fly ash, you have a raw fly ash. You cannot use raw fly ash directly as a catalyst. So some treatment method is required. So what we did, we took raw fly ash well, and we defined as an uncalcined, untreated as a FAN, natural catalyst, fly ash natural, FAN, and also treated at various temperature to get the calcined fly ash and to improve the activity. And see, all the catalysts, the 5 types, 4 calcined and 1 uncalcined. In all types of catalysts, using all type of catalyst, we have performed the pyrolysis and seen the activity. And before that, we have also done the characterization, that what is the exact temperature at which you can have a high surface area catalyst, this fly ash. Okay, so that Fa 600 means 600 temperature calcined at 600, 700 means 700 degrees Celsius we have calcined, and 800 similarly Fa 800 and 900 degrees Celsius when we calcine it is designated as a Fa 900. So later on, actually in catalytic pyrolysis of plastic waste using this fly ash catalyst, when I shall discuss, I won't refer the temperature. Simply I would say Fa 600, 700, Fa 800 and Fa 900 and Fa in catalyst. So I hope people understand it when I shall discuss this. And these are the characterization techniques of catalyst as well as fuel oil product analysis. Catalyst characterization, XRD, TEM, BET surface area. What happened? So catalyst characterization, XRD, same, EDX, BET surface area and FTIR. This is the standard, characterization techniques. These are techniques which is used for the catalyst. So all those characterization techniques were adopted to see the, their physical properties. Like XRD, we adopted to see the crystallinity. Similarly, same EDX, same surface morphology and EDX element, surface composition of various elements present in the catalyst. BET surface area, pore volume is as well as surface area we obtained, and FTIR basically it gave the functional group. What happened? I'm sorry, there is some problem. My screen is visible. Excuse me.
Yes, sir.
Yeah.
Screen is visible, but it is
Yes,
not
sir.
working, I guess.
Not working. All right. I can
Yeah.
also see some. I will say it again. That PPT.
Sure, sure.
I hope PPT is now. You can see
Yes.
the PPT now. Yeah.
Yes, sir.
Thank you. Okay. This characterization I was talking. Sorry for the inconvenience. Catalyst characterizations. Then product analysis. Similarly, FTIR. we'll talk about the functional groups and GCFID. We tested, we use this technique specifically to find out the composition, right? Composition of the, you know, fuel oil. Carbon residue test, it talks about the percentage of, you know, solid residue left over as a carbon, right? When we do the analysis of a fuel, if carbon residue is left over after, you know, test, you know, in a carbon in a ram's bottom apparatus, if less than 1% carbon is seen, then it is okay. It can be recommended for as a fuel in the IC engine. But if carbon percentage is greater than 1%, it is found, then it is not recommended. That means this fuel will give more carbon deposition in the engine. So it talks about the propensity of cracking. If you have a fuel oil of higher molecular weight hydrocarbon consisting of higher molecular weight hydrocarbon as well as aromatics with long chain, you know, paraffin, so that has a tendency to break down, and then it will form a finally, you know, giant molecular structure of, you know, hydrocarbon, aromatic hydrocarbon, which will appear as a carbon black and deposit in the engine. So if the percentage is greater than 1%, then we do not recommend. So carbon residue test is very important test methods to find out the, you know, suitability of use of fuel in the engine, IC engines. Flash and fire point, we talk about the, you know, safety during storage, handling and transportation, and also startup in the engine. Flash point, if the flash point is low, then, you know, the startup will be excellent. Even in the winter, if the flash point is low, that catches fire and startup will be better in the, you know, gasoline engine. But if the flash point is very high, then there will be problem of startup in the winter as a normal climate as well. But fire point similarly talks about the fire hazards. If you know, fire point is very low and there is a, you know, temperature is very high during summer, so that fuel is a there is a high chance of, you know, fire hazards if there is a spark or the flame is present near the fuel storage. Okay. So we have to be very careful when we store the fuel, and if you know do not know the fire point and flash point, so you cannot maintain the temperature. So this is very important indicator, right? As and fire point. ASTM distillation similarly, that gives you about IBP to final boiling point, initial boiling to the final boiling point, and various range from minimum to maximum percentage of distillate and particular temperature we plot basically. And when it matches with the our fuel, what we produce, and when it matches with a, you know, for gasoline, diesel and kerosene, aviation turbine fuel, all the fuels have a, you know, standard distillation characteristics. ASTM distillation, ASTM stands for American Society for Testing Material. So they have their characteristics of a fuel percentage distillate at particular temperature. Suppose 10% distillate temperature you must get at you know, let's say 40 degrees Celsius. So 30% distillate you will get at 70 degrees Celsius. So if you do not the unknown fuel do not match with this, so you cannot recommend. Even if you get a gasoline, do this ASTM distillation and match with the standard ASTM distillation characteristics that is available in Paris handbook. And if it matches with the standard fuel and your gasoline that is being claimed by the, you know, petrol pump, then only you can say yes, it is gasoline. But many times we see there is a deviation because the standard is never maintained, right? API gravity, it is defined by the American Petroleum Institutions, and API gravity basically magnify the specific gravity. Basically specific gravity normally less than 1 for, you know, crude oil or petroleum products, and that specific gravity range is very narrow for, you know, different components of a hydrocarbon. If you use API gravity equation, then it will magnify and you can make that, see the differences. Okay. Gross calorific value will talk about the enthalpy content, how much energy it will liberate during the after combustion. Okay, and higher the calorific value, better is the fuel. So these are all important product analysis that will help you to you know, finally conclude whether this product pyrolysis is suitable for engine or not. This is the experimental setup where you can see one nitrogen cylinder is there to purge nitrogen and maintain inert atmosphere within the reactor. This is basically reactor. This is basically the reactor, and within this reactor, we feed the plastic, in a we cut into small pieces and then feed in the reactor, and it is closed basically, and then nitrogen is purged. And what happened after purging nitrogen? And remember, it is not continuously fed. Sometimes some research they do continuously nitrogen is fed, but we never fed nitrogen continuously. Once the reaction starts, pyrolysis temperature reached, then we stop, because it is to maintain the inert atmosphere. So to ensure initially that oxygen is there, and so oxygen need to be replaced, so nitrogen is purged. Otherwise, that oxygen might create a problem in the sense combustion within the reactor, because oxygen is there, high temperature, and fuel is there, so combustion might take place. So to replace the oxygen, remove the oxygen within the reactor, nitrogen is passed initially, then reaction we start. And there are various reactor arrangements, and that I will tell you later on. But before that, let us see this condenser arrangements. So condenser is water condenser and followed by another condenser which is covered with the ice. So there is a slow reduction of temperature was adopted in this process, because if you do not use this water condenser followed by even ice condenser, let's say any one condenser you are using, so most of the condensable gases will, condensable vapor will escape because of the low residence time. So here slowly, gradually temperature is reduced to trap all the non-condensable condensable vapors, and non-condensable gas you cannot trap, so that will escape from this and will be stored as a fuel. So condensable is liquid, will be collected as a liquid, and non-condensable will escape. So what are the reactor arrangements? Thermal pyrolysis, there is no catalyst. Catalyst in vapor phase, there is no catalyst in the liquid with the plastic, only vapor phase at the top. Then catalyst in liquid phase, no vapor phase catalyst mixed with the plastic, that is B type. And A type at the vapor phase, catalyst bed is installed, and both multi-phase vapor and liquid, that is C type. In catalyst we add in the feed as well as bottom as well as in the vapor phase, okay, using a catalyst bed. So these are the three reactor arrangements: A type, B type, C type. And thermal pyrolysis, where there is no catalyst. So to compare which process is better, right? Now for any reactor selection, there is an L by D ratio. You cannot take any dimension of the reactor, or that means diameter or height. So there is a L by D ratio. When we take basically 1.5, 1.2 to 1.5 in this range for better vapor circulation. For low L by D ratio, restricted circulation. Greater the L by D ratio than 1.5, then circulation path will be higher. L by D ratio, when greater than 2, you need impellers for proper fluid motion. So L by D is maintained 1.2 to 1.5. And we also took in the range of 1.2 to 1.5, right? So these are the reactor bed arrangements. I told you A, B, and C type. So thermal, then A type, vapor phase, B type in the liquid phase, catalyst and plastic, and C type, both the phases, means vapor and liquid phases, were placed. First one is thermal pyrolysis. The result you can see for polyethylene, polypropylene, and polystyrene thermal pyrolysis. Let's see the result of polyethylene. So I am showing here temperature 700 degrees Celsius. 700 degrees Celsius result. Why I am presenting here? Because with the increase in temperature, sample was taken 550 grams and temperature was increased. 700, if you can see, giving 68.2, and 800 giving very high yield, 72.66, but it is waxy. Waxy means higher paraffins are more. Higher the paraffins, see 20 onwards, a semi-solid means that separates as a waxy wax crystals. So higher paraffins are more, that's why it is waxy in nature, not preferred as a fuel. But when the temperature is maintained 700 degrees Celsius, we get the liquid products. And 700 degree fuel, when we analyzed, got flash point low, fire point is also low, carbon residue less than 0.28%, and density, API gravity, calorific value is quite better. So this is solid residue, black char, and pyrolysis oil you can see as a liquid products, little brownish. But as we use polyethylene, so color is different from the this polypropylene, right? Because of different composition of products, different composition in the sense of hydrocarbon is present in the oil. Again here, with the increase in temperature, 700 up to 700 liquid, and high yield is 86, but highest yield was obtained at 800, but waxy in nature. At room temperature, it freezes basically. Okay, it solidifies. So what is the reason? When we increase the temperature, the product which is formed from the polyethylene, from a big polymer, when the polymerization and then secondary reaction takes place, then what will happen? Further, you can say cracking takes place. The larger molecule do not get the time to be there in the reactor for further cracking because of the high temperature. So immediately it will escape. Lower the temperature, it will get time, okay, for further conversion. But because of the very high temperature, it immediately will escape, from the reactor. That's why the larger molecular weight hydrocarbon remains in the liquid, and we get waxy like product. So 700 is the optimum temperature. Similarly, for polystyrene also we got 700, 96% yield. Here 800 temperature, it gives waxy. So we stopped. That's why beyond 80 we did not perform. 700 is the optimum temperature for thermal pyrolysis, and we have the result. And we analyzed also in terms of BTX, and that I'll discuss later on. ZSM5, now catalytic pyrolysis was performed using ZSM5 and fly ash. First ZSM5, let's see the result. Heat to catalyst ratio is very, very important. So 20:1 was used as a obtained as a optimum heat to catalyst ratio. So 10:1, 20:1, 30:1. So with the increase in heat to catalyst ratio, what you can see, heat is increasing, so catalyst is decreasing here. But here is the optimum ratio is the 20:1. There is a balance between amount of area available for the active sites available for the interaction of the molecules, or polymer first and then the product molecule with the catalyst is highest for 20:1 ratio, right? So lower one does not give so much feed to catalyst, 10:1, right? Here 20:1. So here feed is low, catalyst is high for 10:1. But more the catalyst, that does not mean you will get better interaction. So you need sufficient amount of feed material as well. So when you increase little bit amount, give more feed, that availability of molecules becomes higher. So that's why you get better quality of products, better yield, better liquid yield. So here 57.95, you have a lot, more amount of catalyst, but feed is less. Here, catalyst and feed, here is proper mixing or proper interaction you are getting here. You can say proper interaction with the catalyst sites and feed. That's why 58.6. But if you compare with the thermal, there where you have noticed probably that around 80%, 90% or 90% and above, liquid yield was obtained. Here liquid yield is low for polyethylene, and similarly polypropylene 81.23 and polystyrene 86. For all these three feed, liquid yield has gone down, and gaseous yield is increased. That I discussed at the beginning, introductory part, that catalytic pyrolysis at low temperature will give you less yield, but quality is better. But gaseous formation of will be more. Gas will be gaseous, and this is also a fuel basically. Gas, what is coming out non-condensable, is also a fuel. So yield calculation very simple. Liquid yield, gas yield and solid yield, I have just shown here how it was calculated. Liquid yield and aromatic content in pyrolysis oil, that is, qualitative analysis. So pyrolysis, if you see the three types of reactor arrangements, so thermal 68.02, and catalytic A type, that is vapor phase, B type liquid phase, and multi-phase, here what we observe, 46.36. Liquid yield is lowest, gaseous yield is highest here. Okay, even char is also very low. That means when you place catalyst in both phase, liquid and vapor, vapor phase both, you get lower amount of yield, okay, highest amount of gas. But if you analyze benzene, toluene, ethyl benzene, xylene, 39.47, highest amount. So thermal pyrolysis, if you compare with, let me take the marker. If you compare with this, this thermal pyrolysis, this is only 10.75, and here you can see 39%. But C type, that is multi-phase, so quite high, huge jump, 30% more BTEX you are getting. And when A type means vapor phase, if you compare with the vapor phase, this is liquid phase, even there is a huge gap, means highest is always for multi-phase, for polyethylene. Similarly, polypropylene, it is found that catalytic multi-phase you get 82%, right? And where C type, if you compare in terms of BTEX, right, 53.09, here it is only 30% for thermal pyrolysis. If you see thermal pyrolysis, okay, 30.9, but here C type is giving highest percentage of BTEX. But you can say that 15.92% is benzene. In all the cases, benzene is highest amount, yes. But catalytic B, xylene is xylene. Here these are xylene, right? But catalytic ABC, if you see that benzene is also very high. Highest, won't say highest, but very high. But xylene is highest among all aromatics. But benzene is not considered as a fuel component, right? If you see the kerosene, diesel and gasoline, always less than 1%, not considered as a fuel. It is having a problem of carbon deposition, high carbon hydrogen ratio. But if you use directly this fuel without removing or separation of benzene, that will create a problem. So benzene can be separated and used as a chemicals for other product manufacturing, right? So otherwise, toluene, ethyl benzene and xylene, there is no problem at all if it remains in the fuel. Similarly, polystyrene, you can say 26.86% here, and thermal pyrolysis 13.58. So highest is obtained for catalytic C type, and A type, B type is lowest here. So 83, you can say that 83% and 96% thermal pyrolysis. So quantitative, we can observe that quantity has gone down, but quality wise has improved in terms of aromatics. And this is the reaction scheme. Already I have discussed you how to get the aromatic. Next one is fly ash. It's very interesting. Fly ash will give you the informations was used as a catalyst here, and again I told you it was calcined, and this same EDAX image shows that various temperature gives various surface morphology as well as silica alumina ratio. So with the increase in temperature, pores are opened up, and that's why pore volume increases. And finally, beyond 800 degrees Celsius, when the temperature was 900 or maintained, pore collapsing. The fine pores, which is not visible here, but in this figure you can see these pores are visible, large pores. That due to the collapsing of pores, and that's why in the second slide, this slide, you can see analysis, BET analysis and silica alumina index, when we compare, it is seen that Fa fine 800, Fa 800, it gives highest silica alumina ratio, because the pores are opened up at 800 degrees Celsius, and you get the surface area, that's why highest 310.4, and at 800, 850 and 900 degrees Celsius, surface area becomes very low, because pores are collapsing, right? Pore walls are not visible, pores wall get collapsed. That's why also you can see that silica alumina ratio also go down from 16.03 to now 1.43. So Fa800, we can calcine the same catalyst to get a better catalyst in terms of surface area and silica alumina ratio. So when this catalyst was tested in place of ZSM, what we observed, that FAN natural catalyst, thermal pyrolysis first of all 10.92, and FAN natural catalyst 12, has increased little bit. In terms of benzene toluene, I am talking benzene BTX, I have just shown here for better understanding. And C type, you can see 22.11, highest amount. So C type always giving C type. Okay, so for 5 catalysts, FAN, FA600, FA700, FA800 and FA900, all 5 type catalysts were placed in 3 different types of arrangements. So among all 3, if you compare, C type is always giving highest yield here, right? And in every slides I have shown the diesel, kerosene and gasoline comparison with the product. Similarly, polypropylene C type, we using FA800 gives best quality of oil in terms of BTX, and highest you can say BTEX. Similarly, polystyrene 20.93, Fa800 and C type, right? In comparison A and B, even thermal pyrolysis. Now, stability and regeneration, it's very important part. When you talk about catalyst and stability really playing should be checked. And we tested the catalyst first run, second run, third run, and then regenerated. So if you see the regenerated catalyst, this very similar to phase catalyst. This is phase catalyst and regenerated. And in between this used catalyst black, because coke which is formed, that is that deposited on the surface of the catalyst. That's why it becomes black. So ZSM5 and FA800 catalyst, both the catalysts we have compared. You can see the color. This is fresh, and after regeneration we get this one, but this is used one. How it was regenerated? 550 degrees Celsius in a maple furnace, it was burned. Okay, to remove the coke first, it was burned for 30 minutes at 550, and then calcination was done, keeping in a crucible under lead and inert atmosphere using nitrogen flow for 5 hours. Okay, what we got? We got this this type of catalyst which looks like a fresh catalyst. So this is same images used, right? This is fresh, and this one is regenerated, and in between it is used. So by visual observation, you cannot differentiate to that extent. But BT surface area, when we analyzed, we observed F800, the trace catalyst, I told you 310 around 310 meters square per gram, and if you compare with the used, the 215 meters square per gram, it is lower than the fresh one. Then when regenerated and fresh one almost same, 310 and 305, because you cannot remove all the blocked sites by simply combustion. So that's why little very minute change, fresh and regenerated. Similarly, ZSM5, fresh one 400, and 390 regenerated one. Then what we did, we performed the catalytic pyrolysis using A type, C type. I have shown here A type and C type. Just look at the C type. C type, because C type giving the best yield in terms of BTX. So consider the C type. Just for comparison, liquid yield F800 first run 73, 71 second run, and here it is 69. After regenerated catalyst, you see, it has increased. So 73 and 73, first one, even, fresh catalyst giving almost same result. You can say little bit improved, and this change I can say little, minute error maybe in calculation, right? Otherwise, some logic you have to give why the yield is now better than the fresh one after regeneration. Maybe activated, the catalyst now more activated than after regeneration, and active sites are more. Or you can say that there might be my minimum error, because 0.12 and 0.35 there is hardly any difference, right? Similarly, ZSM5, if you see the catalyst, this C type for ZSM5, you can compare this C type. I am not talking A, because C type is the best one, and liquid yield 46.36, right? And here you can see 44.97 decreasing, 43 decreasing, and regenerated catalyst just like a fresh catalyst giving the result, right? Liquid yield. Similarly, BTX also you can see 39 decreasing, and here final one 40.97, and it is 41.11. So it means that fresh and regenerated giving almost same result. However, first, second, third run up to you can see there is a constant decreasing trend in liquid yield as well as in terms of BTX also decreasing. Okay, so this is simple overall conclusion from the study. There's maximum liquid yield and aromatic content for thermal pyrolysis of polyethylene, right? 60.8 and 10.78% for polypropylene. 86.34 it is liquid yield, and aromatic content we got 30.9, and polystyrene liquid yield 96 and aromatic content 13.57, right? While obtained. Okay, maximum BTX yield for catalytic pyrolysis, this is for thermal. Now BTX for catalytic pyrolysis, C type we have compared, because C type is the best using FA900. So ZSM5 is also there for FA900. Liquid yield 22, sorry, BTX I am showing here. So 22.11 for polyethylene, 43.43 for polypropylene, 20.93 for polystyrene. Whereas ZSM5, okay, maximum BTX you can 39.47, 53.09, and 26.86 for polystyrene. Okay, so of course if you compare FA800 and ZSM5, there is a difference in BTX yield, but better than thermal pyrolysis, higher than thermal pyrolysis. After certain modification or using some different support material, we can improve the catalytic activity of fly ash synthesized catalyst, or we can treat with acid to increase the catalytic activity. Okay, the test result for catalytic activity increase indicates that commercial ZSM5 and synthesized F800 catalyst is stable up to third run, and there is a slight change in liquid yield and BTX content. Regenerated catalyst showed similar results as that of fresh catalyst. This is another observation. Physicochemical properties of the pyrolysis oil shows that it can be used as alternative fuel and as a source of valuable chemicals such as benzene, toluene, ethyl benzene, and xylene. So this is a first part, chemical conversion. By chemical, using a chemical route, we can have a energy from waste material, but energy content material, right? Next one is energy generation via electrochemical route, right, from some energy material. And energy, energy production via this alternative route, of course, will protect environment and providing energy security in better way. Okay, and already I've told you this method, this part will concentrate electrochemical route. Okay, so electrochemical route, before I discuss, I would say that innovative view of energy supply nowadays is based on hydrogen gas or hydrogen rich molecule. Right? Wherever there is a hydrogen, we're trying to trap we are trying to convert those fuels via electrochemical method to get electricity directly. Okay, you can have a enthalpy, means heat energy as well, but we are talking direct conversion of this molecules or fuel or energy material to electrical energy. So what is the technology? Technology used is here fuel cell technology and fuel cell technology, right? And what are the material here? Energy material, glycerol and ethanol I am talking. Why glycerol and ethanol? There may be hydrogen, there may be ethanol, means other aliphatic alcohols, ethanol, isopropanol, isopropyl alcohol, ethylene glycol. But I have taken ethanol and glycerol because they are basically renewable in nature. Acetic acid is also hydrogen content molecule. So where hydrogen and hydrogen rich molecule can be converted via fuel cell technology. But I have considered ethanol and glycerol because of their renewable properties. So biomass and biomass derived chemicals for the electrical energy production via fuel cell technology could be an alternative and attractive option. What are the electrochemical cell? Before I talk about the fuel cell, we should know about a cell. There are two types of cell, galvanic and electrolytic cell. So electrolytic cell, externally electricity is supplied to perform the chemical or electrochemical reaction like water splitting, water electrolysis, electrowedding, right? Or electrowedding method, metal extraction, electroplating, chloralkali plant. Charging of any cell is a electrolysis mode, electrochemical cell, electrolytic mode, right? Galvanic cell, electrochemical reaction gives when electricity. When electrochemical reaction, any sort of electrochemical reaction gives electricity. On the other side, electrolytic cell, you need to supply electricity to get the electrochemical or electrochemical reaction at the electrodes, right? Primary non-rechargeable battery, when it gives electricity, right? That is also known as a galvanic cell. Primary non-rechargeable battery, use and throw, when it gives electricity, it's a galvanic cell. Secondary battery, forward mode, when it gives battery electricity, it is a galvanic mode, right? When you are charging, it is electrolytic mode. Fuel cell is another class of galvanic cell where no need of charging, only fuel like hydrogen and oxidant is required. Hydrogen, or in place of hydrogen, methanol, ethanol, glycerol, or acetic acid, hydrogen rich molecule you can feed, you can have electricity. And oxidant is used as oxidant is basically oxygen. What are the advantages? Efficiency, high efficiency, okay, simplicity, silence, no emission or low emission. You can see here in this diagram, one is electrolytic mode. When there is a load, that means it is a battery mode. And when there's a battery is applied, this is a symbol of battery. Okay, this larger arm is positive and smaller one is negative, and this is the symbol of battery. Okay, this external power source. There will be production of oxygen, water electrolysis. There's a very simple example of electrolytic cell. Oxygen will be produced at anode and cathode hydrogen will be produced. And the reverse mode, hydrogen electrode, now if you remove the battery source, hydrogen electrode will act as an anode and oxygen electrode will act as a cathode, and hydrogen will split, will give you electron and ion. Electron will flow through the outside circuit and come at the cathode, and ion will pass through the electrolyte, come at the cathode and give you water as a product. And this flow of electron will be is a current for fuel cell mode. So this right hand side, this is electrolytic mode and this is fuel cell mode. Same cell in a reverse mode giving electricity, and in forward mode it is producing hydrogen and oxygen. So fuel cell is nothing but a electrochemical cell, and where change in gives to energy gives you electricity. What is del G? Change in gives to energy. If overall gives to energy of a any reaction It may be at anode, at cathode you can consider, or from the overall reaction. If you have this type of reaction, you can also calculate change in Gibbs. You can calculate E. E is the potential here. N is F is the Faraday's charge constant, that is 96485 coulomb. N is the number of electron involved in the reaction. So if you see here this cell, if you see this cell, okay, already I've told you, in between anode and cathode there is a basically electrolyte. Electrolyte is nothing but proton exchange membrane, that is nephron, which conducts ion. So membrane may be acidic and alkaline. Like battery, we have seen that it may be acidic electrolyte or alkaline electrolyte. So here I am presenting the proton exchange membrane fuel cell, where there is a PEM is there. It is a very thin membrane, just like a paper is there in between anode and cathode. Hydrogen is fed at the anode, and cathode oxygen. Hydrogen fuel, I already told you, will split, give you electron and ion. And electron, you can see this reaction, anode reaction, and this is the cathode reaction, where electron, ion and oxygen combines, gives you water as a product. And flow of electron, which glows bulb, as soon as bulb, due to the flow of electron. Fuel cells, other way you can say electrochemical device that converts chemical energy of a supplied fuel into electrical energy, and by oxidation and reaction. And apart from electrical energy, you get heat as well. And catalyst is also required in fuel cell. But the electrode is, it has a special properties or characteristics. It is made of a active catalyst, which is nothing but a platinum based, or platinum for PMFC. Okay. So these are the some device or their application of fuel cell. You can see fuel cell generator, just like a inverter power backup system, and then fuel cell bus. You can see that fuel cell installed at the top of this here rooftop. And recently in Germany there was a trial of fuel cell driven train, hydrogen, using a PMFC stack. Okay, in one time charging of hydrogen gas, it could run 450 miles. I hope you understand. And there is no pollution, only water is the product, and electricity is produced using this technology. But the problem with the fuel cell is, that pure hydrogen is required. Otherwise, it will poison the catalyst. Mostly, we produce hydrogen via syngas, via reforming from hydrocarbon to syngas manufacturing COH2. But COH2 separation is very, very important. Removal of CO, that basically add cost. And CO is the contaminates the fuel, poison the catalyst. Okay, and that's why if you have a other route like electrolysis route, where you have a solar electrolysis using a solar photovoltaic, get the DC and then use electricity there to split water molecule, then it is completely renewable nature. You no need to depend on the AC electricity to split the water molecule using electrolytic cell. Similarly, fuel cell car is also now launched in many in global level at various company. So types of fuel cell: alkaline, you can see alkaline, proton exchange membrane fuel cell, direct alcohol fuel cell, phosphoric acid fuel cell. These are low temperature cell. You can see their range up to 200, not more than 200 degrees Celsius. Molten carbonate and SOFC, temperature range is very, very high, 600 and 500 to 600. So that's why the benefit of high temperature is that you can directly use a hydrocarbon where there is a reformer at high temperature, which will produce COH2, and directly you can use COH2 as a fuel in the SOFC. And MCFC also you can use as a hydrogen as a fuel. And these are the reaction. I'm not going in detail of that. You can see anode reaction always giving you electron, or in all anode reaction. And remember, fuel is always fed at the anode side, and cathode side oxygen. Okay, so anode will produce electron, and in cathode it will combine. But if you compare with the alkaline and acidic cell, that flow of ion is from cathode to anode in case of alkaline. So ion is produced at the cathode side, and that will move from cathode to anode. But here, anode to cathode, you can see that H plus ion, which is produced at the anode, it is combining at the cathode. So anode to cathode, there is a flow. And here it is combining alkaline fuel cell at the anode side. Okay, this is the direction of flow of ions for acidic and alkaline. Otherwise, all the cell you can see here it is producing the mobile ion is the H plus ion for phosphoric acid. For alcohol fuel cell also H plus. Carbonate ion is the here mobile ion. O2 minus is the mobile ion for SOFC. So low temperature, high temperature, hope you understand, and they are different power wattage produced by the cell, that is also mentioned below. So all types of cell, what I discussed just before just previous slide, you can see direct methanol and direct glycerol fuel cell is very low temperature range, and I told you that it is a renewable nature. But all types of fuel cell, the major components are electrode, anode and cathode, then electrolyte, current collectors, and bipolar plate. So anode and cathode, electrolyte is very, very important. Bipolar plate, there is a standard design, is a flow channel which basically helps to flow the fuel at anode side, at cathode side oxygen. Otherwise, electrolyte which is there, it may be acidic or alkaline depending upon the nature, type of cell you are going to construct. Sometimes alkaline medium favors the reaction kinetics, and but as such alkaline membrane or electrolyte are not available commercially in the market. So there are many research ongoing to develop or synthesize alkaline membrane. So as such commercial membranes as this alkaline type not available. So acidic membrane, that is proton exchange membrane, PEM, Nafion by DuPont, it's the only you can say proprietary products available in the market. There are many other company, Gore Chemicals, Ashai Chemicals, but their conductivity is not so high as reported by as it is we can have from the Nafion. So Nafion gives highest conductivity, that is in the range of 0.1 Siemens per centimeter. Okay, so Nafion is considered as the best membrane electrolyte, solid electrolyte for the fuel cell. Why glycerol and ethanol? Glycerol, ethanol, it's preferred over hydrogen because hydrogen storage, pure hydrogen, one problem is there. Then it is a storage problem, highly explosive. If you consider AFC, even liquid alkali based electrolyte, then form basically bicarbonates. And if you talk about methanol, that is basically neurotoxic in nature. So all the fuel cells have their own demerits. So hydrogen PMFC, storage problem, alkaline fuel cell, if you talk about that electrolyte matrix get destroyed. If there is a liquid alkali, because solid alkaline membrane not available, CO2 reacts with alkali, it will form the bicarbonate. Methanol is neurotoxic. It is not primary fuel. So ethanol, what are the benefits? Renewable nature, non-toxic, okay, and fermentation of sugar containing raw material is used for the production of ethanol. So it is renewable in nature. Glycerol is the byproduct of biodiesel. It is a non-toxic and renewable in nature. So byproduct of any process is really is a good option to use it for the energy production, right? Ethanol and glycerol properties I have mentioned here. Okay, if you see the boiling point range, it's low, but glycerol is little higher. So fuel cell, when it is operated at low temperature, there is no issue. Okay, so we can operate. What is the route? Sugar containing biomass resources, fermentation, it gives ethanol, and glycerol, 3G triglycerides, methanol, and alkaline or acidic catalyst. When it reacts, it gives you biodiesel, methyl or ethyl ester, and then glycerol as a byproduct. Okay, these are the two routes for two different alcohol renewable fuels I have mentioned here. So combustion of this or electro-oxidation, both routes are available. Okay, electro-oxidation and combustion. However, combustion of a ethanol or glycerol have a certain drawbacks. Okay, but here in electro-oxidation directly you can have the electricity. But here to get the heat energy, what are the drawbacks? First of all, low calorific value than diesel and petrol. It's a corrosive fuel. So ethanol, that's why it is not directly used as a fuel. And there are nowadays a fuel blended with ethanol like 5%, 10%, 15%. Okay, E5, E15, E10, E20, and government of India now recommended 5 to 10 in this range to use the blend ethanol in the gasoline to save the fossil fuel. Okay, but to go up to 100%, it's a modification in the engine is required. And nowadays you can see the fuel price has gone up. That's why government is thinking either blend ethanol in a fuel, gasoline, or ethanol you can recommend to use it as a fuel in the fuel cell to get the electricity, and then using a motor you can use you can use it for moving the car. Similarly, drawbacks of glycerol: low calorific value, high self ignition temperature, highly viscous at room temperature. That's why they are not recommended directly. However, ethanol is being now used as a small small amount, to a small not to a high extent, only a small amount of ethanol. So these are the few points we have to remember. Next is electro-oxidation. Electro-oxidation gives water as a byproduct and CO2 as a byproduct, as CO carbon is there in the glycerol and ethanol fuel. Okay, direct route for electricity generation, it's good. Low emission of pollutants, gases, only CO2, only carbon is there. But same fuel, if you burn, NOx production will be there along with CO2. No moving parts, silent, smooth operation. I am talking of fuel cell. If you don't want to use in a car, directly for power generation, DC, and then you have a converter directly used for all the household devices, electronic and electrical appliances. You can use it to run the all those appliances using a fuel cell. Low maintenance. This two calculation will help you to understand how to find out OCB. Del G equal to NF. This equation already I have mentioned. So E naught is del G by NF. So if you know overall del G change for a reaction, and then N as the number of electron, where you can see that 12 electrons are there. So 96485 is the Faraday's constant. So you can find out that 1.1 to 145 volt you can have for ethanol, and for glycerol similarly 1.21. So 1.21, 1.145, quite high voltage you can have from this to fuel. But we do not use together, we use differently. Okay, ethanol and or either ethanol or glycerol. Of course, the catalyst will be different then at the anode side, because cathode side is fixed. Cathode side is oxygen, oxidant is oxygen. So cathode for both the fuel cell will be same. However, anode will be different as you are using different fuel. So there are many other uses. I have shown here the route of glycerol manufacturing is a byproduct of biodiesel. I already have mentioned, and main product is the biodiesel, and byproduct, what are the uses? Various chemical manufacturing, and then second one I have mentioned here for the use in fuel cell to generate electricity, right? Similarly, ethanol can be used as a chemical, as a hand sanitizer, medicinal solvent, antimicrobial, preservative, and in an IC engine also, that I have told you, through chemical conversion route. But electrochemical route will give you electricity. You can see anode reaction, it gives electron, 12 electron. So one molecule of if it reacts with 3 molecules of water, it gives 12 electron, quite high, large number of electrons is produced. All right. Ethanol and glycerol, if you compare that, potential is 1.145, already I have discussed 1.21. Okay, and efficiency is 0.97, here 0.99%, right? Del G by del H, if we compare, that is called the thermodynamic efficiency, is quite high. So alkaline and acidic, both the routes you can choose to split, glycerol. And what are the catalysts? If it is alkaline medium, so alkaline medium, palladium, platinum, aurum, they are the suitable catalyst. And anode reaction, you can see 14 electron is produced. But the main problem is the intermediates. Some reaction might stop at at the intermediate stage, and then you cannot have 14 electron. So partial oxidation will give you 10 electron, and complete reaction will give you 14 electron, right? So this is the overall reaction for glycerol. Okay, so 14 electron will be produced maximum if it is a complete reaction. Similarly, acidic reaction, their path will be different. As the medium is different, only path will be different, and catalyst is same here, platinum catalyst. But earlier, 3 different catalysts we have shown: palladium, platinum, and aurum. Here on platinum catalyst in acidic media of glycerol, again here also gives 14 electron. But what is the difference here between acidic and alkaline? Only the intermediates formations, right? These are means typically if there is no poisoning or deactivation of the catalyst in between, then 14 electron you can have. But it is not possible to have 14 electron and to complete the reaction. Always we have seen through our study that at intermediate step the reaction gets stopped. Okay. Similarly, ethanol, alkaline medium and acidic medium, both I have shown here. So alkaline medium, you can see 12 electron. It is number of electron produced is same. Only the change, the difference is in the route. Okay. So route various steps, takes place at various electrode potential. If the electrode potential is different, right? At anode reaction takes place at high electrode potential, that is not desirable. So electrode potential at which the reaction takes place, that is also very much important. This is acidic reaction, acidic medium, 2 parallel consecutive path it follows. And if you want to have a CO2 is the final, CO2 is as a product, then these are the intermediates formation will take place. And if acetic acid is the product, we have seen acetic acid is the product, intermediates products, and CO2 formation is almost nil. That means the present catalyst, platinum catalyst, is not suitable to split the ethanol to completely to get CO2 as a final product. If CO2 is a final product, then we can have 12 electrons from the reaction, but that is not possible. So we need a catalyst which can split carbon, ethanol molecule, because carbon-carbon bond is there in between, this ethanol molecule. That is very difficult to break down. Okay, so from the latest literature or latest study, what we have seen, platinum ruthenium is considered as the best catalyst over platinum or other metal catalyst like aurum or palladium. So platinum ruthenium or platinum T in bimetallic catalyst is more active than pure platinum. And there is a bifunctional mechanism for the bimetallic catalyst. It is well established. Scientific explanation is there in the literature. I am not going in detail of that because I have only 10-15 minutes more. I have to finish it quickly. So this is the structure of the electrode and membrane, right? You can see this is anode side and this is cathode side. Okay. So how these are manufactured, membrane and electrode assembly. So electrode ink is prepared, right? And then it is this ink is painted over the GDL, and GDL catalyst ink coated GDL. Okay, as anode and cathode both we have. Keeping the membrane in between anode and cathode, it is hot press, and we get this type of membrane electrode assembly. So one side anode and another side cathode. Remember, the catalyst side will be always inner side. Okay, in between membrane and GDL, catalyst is there, right? This is the original photograph of the membrane electrode assembly, and this is basically cell. This is basically cell, right? So I'm not talking about the fuel cell functioning. Already I've discussed. Overall performance of a PMSC is governed by catalytic activity, electronic conductivity through a metal, and ionic conductivity through membrane, and porosity allowing the hydrogen and oxygen to it. That means mass transfer. So these three the types of losses we can see: activation losses, ohmic losses due to the ion and electron transport, and activation losses due to the slowness of the reaction, right? Kinetics related to the kinetics, and concentration or mass transfer losses due to the transport of fuel or oxidant at the catalyst sites. Any cell, if you want to find out potential, its difference between cathode and anode. Difference between cathode and anode is the overall cell reaction, overall potential of a cell. But cathode anode both will have some losses. So this losses is known as a eta active, means eta anode or eta cathode. So these losses will we will try to find out for anode and cathode, then combine them for the overall cell. Now, if you see this diagram, characteristics, x-axis is the current and y-axis is the voltage. And if you draw current, your cell potential go down, it decreases because of the losses. First, activation loss will be there, and if you draw more current, activation ohmic loss will be there. And if you draw highest current, that then mass transfer losses will predominate. Okay, so these losses can be minimized by designing suitable by designing the proper electrode, and as well as selection of proper catalyst. Okay, so losses controlled by designing parameters and operating parameters. Then if you see the fuel cell reaction, basically heterogeneous type. The catalyst which are there in the within the electrode, this is the electrode structure, where there is a catalyst and fuel will interact at the catalyst surface. The three-phase contact is very, very important. Wherever there is a catalyst, fuel will go and interact with the catalyst, and H plus ion will be formed. At the same time, there must be ionic conductivity path from the catalyst sites to the electrolyte, right? If this is your electrolyte and there is a reaction at the catalyst sites, so ion must pass through electrolyte and then come at the catalyst sites for the cathode. Similarly, for the anode, once the H plus ion forms at the anode side, it must pass through the electrolyte and then reach to the cathode. So as it is a cathode diagram, it is shown only for the cathode. So ion is coming from the anode side to the cathode side through electrolyte, and then the electrolyte present in the structure of the electrode will help to reach the ion at the catalyst sites, right? And oxygen will also reach from the outside to the catalyst sites. So H plus ion electron, which is coming from the outside circuit, and also must have a part for the electronic conductivity, and then it will reach at the catalyst sites. So electrolyte can never transport electron. Similarly, metal conductor can never conduct ion. So ionic electronic conductivity both must be there at the catalyst layer. That I have tried to show here. So catalysis, one is catalysis, and second one, electrode design and fabrication method, we can improve the performance. Okay, so this is hydrogen oxidation reaction I have shown. I am not going detail of that. Let us move to the this rate equation. So if you see the rate
we
equation,
will find up in 5 minutes, sir.
Yeah, sure. I am going to the rate equation. If you see the rate equation for a fuel cell, right? This is basically as a function of concentration of fuel, gives energy, and temperature. So more the concentration, more will be the kinetics, or we can have a high current. Then gives energy, lower barrier is lower the barrier of the gives energy, then higher will be the rate. Similarly, temperature is high means, you will have a better kinetics or better higher current. Higher the kinetics, better is the current, higher is the current. And if the temperature is high, kinetics will be higher. Increasing the number of possible reaction sites by suitable design of the electrode, we can do that. Then I shall talk about the selection. If you see how to select the material by knowing the J naught is highest for platinum, rhenium, aurum, and because A and H, metal and hydrogen bonding is intermediate range. That's why J naught will be higher, right? If his bond is so strong between metal and many atoms, then current will be low. Even very low bond between hydrogen and metal and hydrogen will give you low current. You can see this and this region will give you low current because of low strength and high strength will give you, there is a low interaction. That's why no transfer of, electron there. High interaction that won't release the hydrogen. That's why less current. But intermediate binding energy or bond energy will give you higher current density. So how to improve the kinetics? Increasing the temperature, increasing the reaction sites, and we can increase the reaction sites by proper fabrication techniques. These techniques are rolling, printing, spraying, etc. Again, I have shown you a three-phase contact. I am not going in detail of that. This is a actual, image of picture of my fuel cell setup, and I have finished it. Okay, so let me arrow. I will just show you the fuel cell functioning. Anyways, you can see this video is not opening, some problem. Okay, it has opened now. You can see this. This is a fuel cell, hydrogen fuel cell we are having. Only 3 cells. Okay, and simple hydrogen cell stack in series. All right, very small foray. Okay, and we are getting the current which is sufficient to glow large number of LED, but we have shown here only 3, right? So this is a original PNFC where hydrogen is a fuel. Okay, so this is a real setup. This is another setup for ethanol or methanol fuel. Okay, so just to give you real experience of a fuel cell. So this is my paper, published paper, publication, and this is my research group, PhD and masters and UG students working, and many of them have finished. Thank you for your kind attention. If you have a query, please, you can ask me. You're welcome.
Thank you, sir. Thank you very much for this informative talk. You talked about all the plastic disposal, the mechanism of polymer degradation, and the energy generation. It is really a wonderful talk. Thank you, sir. Is there any question? If there is any question, anybody can ask. The participants are requested to ask.
Right. You can also drop me a message. You can email me if you have any query, right?
Yes, sir. Yes, sir. So if there is no question, we will thank Dr. Hiralal Pramanik, sir, for giving this wonderful talk. And sir, thank you very much.
Thank you.
Sir,
thank you once again. Okay.
Sir.
So may I leave now?
Yes, sir. Sir.
Okay. Thank you so much.
Sir. And for rest of the participants, we will join again after lunch at 2:30 for the next talk by Professor Trilok Singh from IIT Kharagpur. So kindly join at 2:30, sir. Thank you.